This is part 2 of Lecture 11 on respiratory physiology. This information can be found in Chapter 22 of your textbook on pages 819 to 857. Gas exchange. As you may recall from part 1, we were worried about or concerned about external respiration and internal respiration. External respiration is the diffusion of gases between the blood and the lungs. Internal respiration is the diffusion of gases between blood and body tissues. Both processes are subject basically to the basic properties of gases and the composition of the alveolar gas. In this table, we can see a breakdown of atmospheric gases. On the left-hand side, we have the type of gas: nitrogen, oxygen, carbon dioxide, and water vapor. We see the approximate percentage of each gas in the atmosphere. Nitrogen being the majority gas at 78.6%, oxygen at approximately 20.9%, carbon dioxide at 0.04%, and water vapor at 0.46%. These numbers can vary within certain margins. In terms of the pressure, we measure air pressure in millimeters of mercury. The total atmospheric pressure at sea level is 760 millimeters of mercury, with nitrogen consisting about 597 millimeters of mercury, oxygen approximately 159 millimeters of mercury, carbon dioxide 0.3 millimeters of mercury, and water vapor at 3.7 millimeters of mercury. In the alveoli, the composition is slightly different. In the alveoli, the percentage of nitrogen is slightly lower at 74.9%, oxygen is slightly lower at 13.7%, carbon dioxide is slightly higher at 5.2%, and water vapor is also slightly higher at 6.2%. In terms of basic properties of gases, this table is demonstrating Dalton's law of partial pressures. Dalton's law of partial pressures expresses that the total pressure exerted by a mixture of gases is equal to the sum of pressures exerted by each gas. So if we were to look at the partial pressure composition of the atmosphere at sea level, and we add up these numbers, we will see that we get a total of 760. Partial pressure is the pressure exerted by each gas in a mixture, and is directly proportional to its percentage in mixture. At higher altitudes, partial pressures decline, but at lower altitudes, partial pressures will increase significantly. As we can see in the diagram on the bottom right, if we have two tanks of equal size and volume with two different gases, and we have one gas which is at 2 atmospheres and another gas which is at 4 atmospheres, if we were to combine these gases into one tank, we would have a total of 6 atmospheres. 2 plus 4 equals 6. The next law is Henry's law. Henry's law basically says that each gas dissolves in liquid in proportion to its partial pressure, and at equilibrium, partial pressures in the two phases will be equal. The most common demonstration that most people can relate to is that of a carbonated beverage. Whenever you open up a bottle of carbonated beverage, you disturb the equilibrium, and that's why you hear the tss of gas escaping. But basically, as pressure decreases, so does the gas ability to dissolve in a liquid. In terms of Henry's law, at a constant temperature, the amount of a given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. On the right-hand side, we can see that we have more gas molecules, and hence, more of the gas will be dissolved in the liquid. On the left-hand side, less gas molecules, less gas is dissolved in the liquid. The amount of each gas that dissolves depends on the solubility and the temperature. In terms of solubility, carbon dioxide is 20 times more soluble than water than oxygen, and little nitrogen will dissolve in water. As temperature of the liquid rises, the solubility will decrease. The alveoli contain more carbon dioxide and water vapor than atmospheric air, so the mixing of alveolar gas occurs with each breath. External respiration, that is pulmonary gas exchange, involves the exchange of oxygen and carbon dioxide across the respiratory membranes. And this exchange is influenced by the partial pressure gradients and gas solubilities, by the thickness and surface area of the respiratory membrane, and by ventilation-perfusion coupling, that is a matching of alveolar ventilation with pulmonary gas or pulmonary blood perfusion. In terms of the thickness and surface area of the respiratory membrane, the respiratory membranes are very thin, approximately 0.5 micrometers thick. And you have a large total surface area of the alveoli, which is approximately 40 times the surface area of the skin. If you were to take the surface area of all the alveoli of both your lungs, they would be equivalent to approximately the surface area of a tennis court. Internal respiration involves capillary gas exchange in body tissues. The partial pressures and the diffusion gradients are reversed compared to external respiration. That is, tissue pressure of oxygen is always lower than the partial pressure of oxygen in the arterial blood. So the tissue partial pressure of oxygen is approximately 40 millimeters mercury. The arterial blood partial pressure of oxygen is approximately 100 millimeters of mercury. Therefore, oxygen moves from the blood to the tissues. Tissue partial pressure of carbon dioxide is always higher than arterial blood partial pressure of carbon dioxide. So, carbon dioxide moves from the tissues into the blood. And the venous blood returning to the heart has a pressure of oxygen of approximately 40 millimeters of mercury and a partial pressure of carbon dioxide of 45 millimeters of mercury. In terms of ventilation perfusion coupling, what we refer to or mean is we mean basically how much air is reaching how much blood within individual alveoli. Perfusion refers to the blood flow reaching the alveoli, and ventilation refers to the amount of gas reaching the alveoli. Ventilation and perfusion rates must be matched for optimal, efficient gas exchange. In terms of the influence of local partial pressure of oxygen on perfusion, a change in partial pressure of oxygen in the alveoli causes change in the diameters of the arterioles. Therefore, when you have high alveolar oxygen pressure, the arterioles open up or dilate. Where alveolar oxygen levels or partial pressure is low, the arterioles constrict or close. This directs blood to go to the alveoli, where oxygen is high, so the blood can pick up more oxygen. The opposite mechanism is seen in systemic arterioles that dilate when oxygen is low and constrict when oxygen is high. In terms of the influence of local partial pressure of carbon dioxide on perfusion, a change in the partial pressure of carbon dioxide in the alveoli causes changes in diameters of the bronchioles. That is, when alveolar carbon dioxide is high, the bronchioles dilate. Where alveolar carbon dioxide is low, the bronchioles constrict. This allows for the elimination of carbon dioxide more rapidly. The goal is to balance ventilation and perfusion. The changing diameters of local arterioles and bronchioles synchronizes ventilation perfusion. And ventilation perfusion, however, is never balanced for all alveoli because of two reasons. There can be regional variations present due to the effect of gravity of blood and airflow, or occasionally alveolar ducts are plugged with mucus, and this causes unventilated areas. And this is the end of part 2 of lecture 11 on respiratory physiology.